So far we've calculated the determinant for a single matrix two different ways. Let's do another example now. We're going to do the next exercise that I've copied onto another sheet. And this sort of illustrates what you're going to have to do on your own or do on testing. So find the determinant of this matrix, and notice that A is a 4 by 4 matrix. So it's 4 by 4 square matrix. And what we got to, if we're going to do this on our own, I have to choose a row or column to expand along. And there are smart choices and not so smart choices that you can make here. I think you probably can already see that if I can find a lot of zeros, that's going to be really going to shorten the amount of calculation I have. So I'm looking for a row or column with lots of zeros, either the first row or the third column. I'm going to choose the first row here. So I choose to expand along row 1. But you don't have to. If you want to be different, or if you're just some sort of like masochist or something, you could pick like row 2 or column 2, and you'll just have a lot more work to do than we have for row 1. Now, okay, let's start writing this out. Determinant of A. Now, I'm not going to write out as much detail as we did in the preceding exercise either, because we really don't need to rely on a formula here. We just got to understand this process. And the symbols don't help us. It's just like knowing the process that's going to help us. I'm going to write my pattern of plus or minus signs above that first row, because that takes care of my -1 to a power. I don't even have to figure that out. So here we go. We're going to get started. So I take the first entry. The first entry is 1. Then I'm going to take -1 to a power, but I know it turns out to be +1 from that plus sign. Then I'm going to multiply by the determinant I get when I remove that row and column. Now I'm going to get a 3 by 3 determinant to calculate, which is still a messy problem, as we shall see. So remove the row and column for the entry 1. I get 706, 630, and 31, -5. So I'm still, that's a whole problem I got to figure out yet, the determinant of that. But now let's move on to the next entry. The next entry is 0. I'm going to have 0 times -1 times the determinant. Who cares? It's all 0, right? I really don't have to write that down. 0 times a +1 times another determinant. It's 0, so I don't even have to write. That's the advantage of finding these zeros, right? All this stuff is 0. All this stuff is 0. But now I do have the entry of 3 times a -1 times a 3 by 3 determinant I get by removing the row and column of that 3 entry. So I get 270, 063, 731. So 1 times 1 is 1, of course. So I'm just going to start calculating this determinant now. Now this is another problem, and I got to choose a row or column to expand along. And since I can't do better than 1, 0, I'm just going to pick the first row again. Yeah, I don't, well, that's fine. Now, I start a whole new pattern of plus or minus signs. And so for this determinant, I write the entry 7 times a +1 times the 2 by 2 determinant when I remove its row and column, 3, 0, 1, -5. And then I get plus a 0, so I don't have to worry about that middle term, plus 6 times a +1 times a 2 by 2 determinant, I get 6, 3, 3, 1, I believe. And now I get plus 0, so I get my 0 stuff. But now on the end, I have another determinant to calculate. And maybe here I'll just, I'm going to go across the second row. Now what will the plus or minus sign pattern be for the second row? You always have to start with the first row, plus, minus, plus. So this second row is actually going to be minus, plus, minus. Notice it'll be minus for the first entry because I'm in the second row coming down. So out in front of everything I have a -3, and then I'm going to need big grouping symbols because I'm going to have a bunch of stuff that all gets multiplied by -3. And I start out with my first entry is 0, so I don't have to worry about it. And then I move on to plus 6 times a plus 1 times a 2 by 2 determinant I get by removing that row and column. So it looks like 2071, 2071. And I'm going to have to come down to the next line here. So I'm going to have 3 times a -1 now, times the determinant 2773, I think, when I remove its row and column, all in that big grouping. So I got 7 times -15 minus 0 plus 6 times 6 minus 9, and all my 0 stuff. Then I have this -3 in front of my big grouping, so I better clean this up a little bit now. I got 0 plus 6 times 2 minus 0. Ooh, I like that. And then minus 3 times 6 minus 49. And now it's just the, process of going through the arithmetic here. What is 7 times 15 is going to be -105. And then 6 minus 9, -3, plus -18. Plus -3. So what happened in my big grouping? I got 12. 6 minus 49 is -43 times 3 is 129. I think is it plus 129? So I got -123 plus -3 times 141. That's going to be -423. And what do I get? -546. I think that's right. Okay, so of course it's the initial first few steps that are crucial, right? The tail end here was just a little bit of arithmetic. We calculated a big messy determinant. We could have picked any row or column, and you always are going to get that number, -546. That's something special about this matrix. Now let's go ahead and we're going to finish there's one more page to this handout for this section. And so whenever we learn a process in this course, it seems like there's sort of this common way in which we learn the complicated way to do something, sort of the official calculation, and then we look at theorems and theory that help us come up with shortcuts to use under certain circumstances. So we are going to start learning about shortcuts to calculating determinants in certain situations. And theorem 2 is our first shortcut. If A is an n by n triangular matrix, remember that definition of triangular from the beginning of chapter 2, then the determinant of A is A11, A22 to AN. That's the product of the entries on the main diagonal. So we love triangular matrices, or things even simpler than that, because it's so easy to calculate the determinant. And for the proof here, I'm not proving it in general. I'm just showing what would happen with a 4 by 4 lower triangular matrix. So it would look something like this, where I know I have zeros in the entries that are indicated. And it's not too hard to see that if I expand along row 1, I'm going to get blah, 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 blah. I'm going to get A11C11 plus a bunch of zeros. A11C11 is just going to be A11 times the determinant that you get by removing that row and column of A11. And now what's A11? Or the determinant of A11? Determinant of A11 is the determinant of this matrix, which you can expand again using cofactor expansion. And you pick the first row again if you'd like, and you're going to get 822 times some stuff. And I think you can see what's going to happen is, because of all these zeros, we just keep lucking out and getting, we just end up multiplying these entries along the main diagonal. So the original determinant we wanted is just A11 times A22 times A33 times A44. So that's true for any triangular matrix. The determinant is particularly easy to calculate. We just multiply the entries on the main diagonal. And then I have an extra theorem that's sort of my own, but maybe the book just thinks it's obvious, but I wanted to make sure that we realized, it should be kind of obvious to you too. If A is a square matrix with a row having all 0 entries, or a column having all 0 entries, then the determinant of that matrix is going to be 0, right? And the reasoning of the proof is just you would expand along that particular row or column, and you're going to end up with 0 times each term, right? So you end up with 0. So I think you would have probably, I bet everybody could have come up with this theorem on their own, but it's just worth pointing out. So that's it for 3.1. We'll start 3.2 soon.